Okay, let's continue our story. And in the last class, we studied this so-called NNM states in double layer system. And so this is the wave function, Z in one layer, W in another layer. And this system have an interesting property that when n minus m equal to 2, or instead in 220 state or 331 state, this kind of double layer exciton, which with charge, fractional charge in one layer and fractional charge in another layer, can be a fermion. So you say, so what? Yeah, you have an excitation which have a fermionic statistics. But when you have excitation with a fermionic statistics, that means you can condense this fermionic excitation into, say, integer quantum Hall states. Yeah, you can create those excitation and make them into integer quantum Hall states. Then you get another wave function, another phase. Well, another phase is this charge 2e Laughlin states. So actually, from here to here, it's really to make this fermion into integer quantum Hall states. That's all we do. They may say, okay, we can also make fermion into p plus ip superconducting states, because those fermions are not conserved. Only Z2 conserved. Their number is not conserved. They are naturally superconductor. And if you do that, you go to these states. Which is non-abelian states. And these non-abelian states also have a fermion excitations. And if you make that fermion excitation into p plus ip state again, then you go to here. So by this two-step p plus ip equal to one step of a filling fraction 1. So basically, this is what this phase diagram is about. And so the interesting thing is that if you do this, you get this kind of very interesting non-abelian states. So that's one way to obtain non-abelian states. So later we'll see this condensation of fermion into integer quantum Hall state or into p plus p states in some other content. Okay, and in the last class, we also discussed a Z2 topological order using this slave particle approach. And but now today I want to start with the string operators. The string operator actually is very important, as you heard from several talk. So in the topological model, so what is string operator in topological model? You know that topological model it have a two term which they all commuting. So the q square and f square equal to 1. So the eigenvalue of q and f with just a plus minus 1. Okay. So therefore, naturally, if a q and f all equal to 1, that's a ground states. If you make one of them equal to minus 1, that's an excited state. So if you make a q equal to minus 1, the excited state, the particle-like excitation called E-type. If you make f to minus 1, it's M-type. So there's a two type of excitation. And then the question is that how to create them. You want to apply a spin flip operator somewhere to create this excitation. But it turns out those excitation cannot be created by any local operator. So that's very, very special. And we need something like a string operator to create them. Okay, what is a string operator? And so here is a string operator. Yeah, remember this. The q in my here is a product of a sigma z on the legs, and the f is a product of a sigma x along a loop. And then the string operator will be the similar. That is, you have a product of sigma x along a line. Just give you a string operator. So this is a one of a string operator. This is the red one. So this WE. So this is a one of a string operator. And this string operator is very special because if the string operator is closed, it commutes with Hamiltonian. Yeah, one can check. It certainly commute with the f term because they all sigma x. It also commute with the q because Q and the string always have a two overlap at two places. And each place give you -1 when you have overlap in two places, so they commute. Okay. So actually, this is in some sense this is a symmetry, but generated by a string operator. So my understanding this is like a higher form symmetry. That's it. So this is a higher form symmetry, just a string operator. So string operator means higher form symmetry. Higher form symmetry means you have string operator or membrane operator. Nothing really. It's a pretty straightforward. I think in this case, pretty straightforward. That's it. And if you really want to push it, I would say that even when you add the perturbation, you still have a string operator. And let me try to see. Yeah, you can still define the string operator, which kind of commutes Hamiltonian. So that's like emergent. This higher form symmetry is already emergent as long as you're in this phase. Okay, so I won't go talk too much about it. But however, when you have an open string operator like this, when you have open string operator, then you'll find near the end, this open string do not commute with the Q, because like on this side, the Q and the red string only overlap at the one link here. One overlap means that they are not commute because Q is a sigma z here. So therefore, this string operator flip a Q here on this vertex and flip Q here on this vertex. So therefore, this open string operator create two E particle, and that's it. So that's why they are related. And similarly, we have same story for the M particle, but here we have to draw the string in the dual lattice. This is very special. So we have the dual lattice is centered as a plaquette. We connect plaquettes. So this blue line is on the dual lattice, and it's product of sigma z. Then this term flip sign at the end of the string with the f, flip f, sign of f. Again, they commute with Hamiltonian if they're closed. Same story. Okay. And then there is a third string operator, which actually is a combination of these two. Okay. And which is but this third string operator can be we can define this operator as an operator on the link, like this red one on the link, with a framing. So the framing is that we have a string, we shift it, displaced by a little bit. So then that's one of framing. So this thin blue line is the framing of this red line. Okay. And this framing cut certain legs. And at those legs, we have a sigma z. So basically, this is a string with hairs. So here another red one is just product of sigma x. Then there's some hairs. The hair is the leg cut by the framing. On the leg, we have sigma z. And in some sense, this is the kind of bound state of a string on the dual lattice combined with a string on the link. That's on the lattice. So there are two ways to see this. So this is the third string. Certainly, this third string is kind of a combination of the first two strings, and at the end of the string also give you a so-called type F excitation. So this is a very special. So those excitation, they carry local energy. The energy are local, particle-like, but they cannot be created by local operator. So that's why. So this is the true meaning of a topological. So topological excitation are excitation which carry local energy, but they cannot be created by local operator. And those excitations are also inequivalent topological excitation in the sense, by applying local operator to one excitation, you never get in the other one. So they are distinct by local operator. So they cannot be connected by local operator. And so that's a string. I describe this really as to say that obviously, the extension have a fusions. If you have 2e together, it's trivial. And you can see that actually square of the string operator give you 1. So therefore, the fusion of a topological extension can be read from the fusion of the product of a string operator. Later, we are going to use this property. And similarly, this F type is a fusion of E and M. And then this also can be obtained as a, so this F type is this is E and M, this is WF. And the F square equal to 1, so that means the product of all 3 string operators equal to trivial. So those are kind of fusion from string, and we can read from the fusion of a particle. So that is a picture we are going to use later. Yes?
The framing, you always pick the 2 lines.
Yeah, there's some try to, yeah, you hope the framing don't cross with the red line. If the cross, you just, I think if it cross, it's also okay. You can make it a cross. Just make, if the framing cross the red one, then at the crossing point, I think this leg should be counted as well. But by displacement is one convenient way to do so. But you can do more general framing. Yeah. So actually, this framing is very important because in some sense we can say that these E and M type are kind of point-like, but F cannot be point-like. Somehow it have this framing. Yeah. Okay.
Yeah, I mean I understand E and M type. I don't quite understand. Why? I understand.
Yeah.
I understand the E component.
Yeah.
Sorry, it's E component, but I don't understand the addressing by the bonds that touch it.
That's right.
Do that or why?
To make the operator commute with Hamiltonian. This actually is quite interesting. For double summing model, you have to dress it like that to commute with Hamiltonian. Otherwise, so there's no hairless string operator commute with Hamiltonian, but they always have this kind of legs. And
They still need to be close.
Don't have to be close, but same thing. The close string operator would commute with Hamiltonian, but the design string operator is very special. It should have these legs.
Sorry, even if it's open but with legs.
No, they don't commute near the boundary, but they commute in the middle. Middle part all commute. So therefore, the energy cost only at the boundary. Yeah.
I have a dumb question, but what happens if you put this on an unorientable manifold? Can you never define the F?
You can define F particle.
I mean, what about the frame?
The
framing change when you go around.
If you go around it, I think you can still define it. It's just it may cross itself once. You allow them to cross itself once. Okay. Yeah, it's a. But the yeah. So now the questions are, so those are particle-like extensions. What is their statistics? We have discussed this using some cartoon picture. So now we want to do something serious. We don't believe in cartoons, so we believe in the symbols. Okay. So what is your statistic? You say, oh, those are bosonic operator. So of course they are boson. But then you realize that this WE operator actually created 2 particles simultaneously. So at least combination of 2 particles is boson. But each one is what? It's difficult. So here is really coming to the question. What is definition of fermion? Are we looking for antisymmetric field or the Grassmann field? We don't have Grassmannian field here. So where's how to understand what is boson fermion? And so the point is that actually the statistics is a dynamical property. Here that's on the emphasize. So it's encoded in the hopping of the particle. If you know how particle hops, you know their statistics. But the hopping operator of a particle actually is a string operator. This open string operator can be viewed as a hop one particle from one end to another end. Applying open string is a really particle hopping. So therefore, once you know the string operator, you know the hopping. And once you know the hopping operator, the algebra of a hopping operator determines statistics. It's a dynamical property. It's a Hamiltonian, kind of like it's in a Hamiltonian. Okay. So the simplest geometry is that you consider hopping among 4 sites, A, B, C, D. There's a 4 site. So we have a 3 hopping. You know, T, B, A is A, B. You log hop from A to B and B to D, and etc. Initially, we have 2 particles at A and D. Okay. And then we first hop from A to B, B to C, then D to B. So then at the end we have 2 particles at B and C. So after 3 hopping, so this 3 hopping is this one, A to B. This hopping times this hopping times this hopping. This 3 hopping operator make these 2 particles to here. However, if in a different order, it's the same hopping, but a different order. We can do the B to D first, then C to B, and A to B. Then you actually, you move 2 particles to B and C, but with exchanged order. Okay. So therefore, they are really same hopping path, just different order. So compare these 2 phases, give you statistics. Yeah. And so if you look at this more carefully, you can see that there's one hopping sitting at the middle. They don't change. It's 2 hopping on the 2 sides switch place. So that's how you compare the 3 hopping. So we call this a hopping algebra. So once you have this, compare their phase, then you can know their statistics. Then for the type E string, then all these hopping operators just sigma x. That's it. So it's here. All the sigma x here. And then there's then clearly this kind of they commute. So the different arrangement of 3 hopping are really the same. It's not different by a phase. So this is how we tell the E particle is a boson, because like the same phase means the exchanging B and C is the same. So however, for type F string, it's a little bit tricky. So we had the hopping operator would have a framing, but we have to be very careful that all those framing should be consistent. So basically we shift these 3 hopping together by some distance. Then we get this kind of framing. So from here you can see that for the hopping A to B, the framing don't cut anything. So therefore the A to B is still sigma x, just like there's no legs. But however, for the C to B hopping, this framing cut the leg 4. Okay, so the C to B have sigma z at 4, the link 4. Then similarly, from B to D, and this framing cut link 3, so we have a sigma 3 here. And so then we just apply this again. It turns out that this sigma 3 here, and there's a sigma 3x and a sigma 3z, they do not commute. And so when you switch orders, so there's a minus sign because these 2 orders switch, so there's a minus sign. So that's a fermion. And this kind of framework works for abelian. I think also works for non-abelian, but non-abelian is trickier. But for abelian, it's pretty straightforward. It's just the phase is not 1 or minus 1, it's some other phase. And actually, this configuration have a chirality. So the opposite chirality have a minus theta plus theta. So they kind of all there. Okay. So this is kind of more theoretical or more rigorous way to calculate statistics. Yeah. So by so-called this hopping algebra. So any question? Yes. All the emergent no, let me put it at least when you have a string operator, yes. Okay, if the topological extension are created by string operator, and then you can compute their statistics this way. I think that's probably true that all the emergent fermions are created by string operator. Even for the one with no string net expression, that's probably true. So, but once you know it's created by string operator, then from the algebra of a string operator, so this also can be viewed as the algebra of open string operator. Then you can determine if the statistics as n. Yeah. Yes. Yes. So this applies to any dimension. Exactly. That's why I thank you for emphasizing this. I thought this is much better because there's two ways to understand the emergence of Fermi statistics. One is a binding charge with a flux, and that is worked in 2 dimensions only. In 3 dimensions, there is a binding of charge to the monopole, but that requires U1 gauge field. So in 3 dimensions without U1 gauge field, we don't know how to produce a fermion. And in higher dimension, we don't know how to produce a fermion. But actually, it's pretty easy if you're using string picture. And this is I think this is a way to produce fermion in any dimension for any gauge group. Yeah. So that's kind of different. But this monopole picture and the flux binding picture probably is a special case of this. Yeah. And so there's a belief that maybe this is universal. So all the emergent fermion can be understood this way in any dimension. Okay, so far it's an example for a topological order. And so next we try to ask more general question. And this more general question is about how to generically probe topological order. It's really like the X-ray probe. To probe a crystal order, you just need to do one experiment, that's X-ray scattering. And you can probe all possible crystal order by performing this one experiment. And so we want to ask the similar question. What kind of experiments you do, or one experiment, which allow you to probe all possible topological order? And the answer we don't know. But we can relax a little bit. What kind of theoretical experiments you do? So today I'm going to talk about some theoretical experiments you do, and then that allow you to probe all topological order. But actually, what we really want to consider is this topological invariants. So what kind of topological invariants we can design which allow us to label or characterize all topological order? So this really just give names, so we have example of topological order, but we want to give them names. You can give name A, B, C, D, F, G, but you can only label 26 of them. And so how to give a reasonable name? And actually, this is very important because if you don't have a name, you have nothing to write down on the paper. You cannot say anything. You cannot do anything. So once you invent a name and a symbol, then you can type into Mathematica and the Mathematica tell you something. So right now here we try to come up with some kind of reasonable name. Then you can do manipulation of those names. That's what we call calculation. Then you can do things. And but since topological order is something new, so we don't have a name. So I had to invent a name. We had to invent a proper name. So that is the key. And so actually, historically, the topological order is defined by this topological invariance, by this probe, not by this long-range entanglement. That's a much recent work. So at the beginning, one of the topological invariant actually is a ground state degeneracy. We have a Hamiltonian, or we have ground state, and the ground state may be degenerate. So it turns out that this ground state degeneracy for certain system are robust against any perturbation. So it's a topological, that's called, we call topological degeneracy. But it depends on space. Like on the sphere, there is no degeneracy. But on torus, there's some degeneracy. On GDS2 Riemann surface, there's a more degeneracy. So there's a topology dependent degeneracy. So that's actually kind of inspired the name of topology order. And so this topology dependent degeneracy, but which is robust against any local perturbation. So this is a sequence of the integer, like a degeneracy on all kind of a topology of space. This sequence integer is a name. Okay, that's a data. So that's one of data which is characterized topology order. And then the next question I want to ask is that enough? If this sequence integer can distinguish all different topology order, then we are done. We already have a proper name. And actually, this is not enough. So we need something more sophisticated. Okay, so how to get something more sophisticated? Okay, and then we have to introduce the notion of so-called moduli space. So what is a moduli space? The moduli space is just a fancy name of a shape of a torus. The torus have all kind of shape, and each shape is one point. Another shape, another point. All these points together give you a moduli space. So when you go through moduli space, you go through different shape of torus. But mathematically, we say that we have a metric on the torus, on sphere, whatever. And we can change the metric, and different metrics give you different point on the moduli space. So that's just a different metric. Okay. And then then we have this topological degeneracy on for each metric. If you pick a metric, you still have a gap. You still have degeneracy. That means for every point of a moduli space, we have a subspace of a big Hilbert space. And this subspace is nothing but it's a ground state subspace. There's a ground state subspace. There's like a four-dimensional vector space for one point. But if you shift to another point of moduli space, then because coupling constant changes, you still have 4-4 degeneracy. But however, the wave function not exactly the same. So it's like another subspace. It's a different four-dimensional subspace, which is your ground state subspace. And that's at another point of moduli space. Okay, so what we get? We get something called a fiber bundle. So this is a picture of fiber bundle. And so the sphere is our moduli space. Our total Hilbert space is a three-dimensional space, which is always the same. But however, at a different point in the moduli space, we have a two-dimensional subspace. Then at a different point, we have a different two-dimensional subspace. And so this the base manifold, which is sphere, plus those vector subspace on every point, this together is called a fiber bundle. So actually, so these degenerate ground states define a fiber bundle or vector bundle on the moduli space. So that's a kind of mathematical fancy way to say this. The real space is a sphere or a torus, but the moduli space is a space of a metric on those manifold. So this is infinite dimensional space. You have all kind of metric, and it's really space of a metric. Okay, so this is seems it's a useless complication. You know, you have even dimensional fiber bundle. You know, it's just a. But however, this is not so bad. And okay, so when you have a fiber bundle, that means when you try to do a so-called parallel transportation, and then you may get this SUN rotation, or sorry, UN rotation. Suppose your vector bundle is n-dimensional. And when you're shifting around, this give you non-abelian barrier space. This is really non-abelian barrier space, which is the UN rotation. But however, only the U1 part have a curvature. by which I mean falling. If you go along the loop, doing this parallel transportation, go around the loop, and then when you go back to the same point, you find that the transformation is not un, it's u1, only phase. The SUN part is always trivial. So it have this property. Then you may ask, why you have this property? Because of following. If you go around the loop of modular space, you have non-trivial SUN twist. That means you can perform some kind of cold atom experiments. You have a time-dependent Hamiltonian, which is just go around this loop, but very fast. This fast time-dependent Hamiltonian, in the cold atom theory, people routinely say this can become effective time-independent Hamiltonian. But the actual term you get depend on this non-abelian Barré phase. If this non-abelian Barré phase contains the SUN part, that means a different ground state accumulate different phase around this loop. Then in this time-independent Hamiltonian, effective Hamiltonian, it will correspond to have different energy, because as time evolves, they accumulate different phase. That means different energy. So that means, but this kind of small loop perturbation is a local perturbation. That means you can using local perturbation to split degeneracy, which you already say you cannot do. This Hamiltonian has the property no local perturbation can split degeneracy. So that means for every small loop you can do, you can only have a overall U1 phase. I mean all the level either shift up and down together. They cannot have any splitting. So there is a U1 phase of this vector bundle. And this if this U1 phase curvature is a U1 phase, is described by some curvature of magnetic field. Go around a small loop, you get the phase, and this phase is like a flux going through this loop. But this magnetic field is a moduli space. There's a magnetic field in moduli space, and that's it. And this magnetic field in moduli space have a very fancy expression, which is a gravitational Chern-Simons term. So that means I won't derive it, but there's a way you can see this. So that means the low energy effective theory would depend on the metric. So this gravitational Chern-Simons term is something depend on the metric. If you know the metric, you can compute this omega 3, and depend on the metric. And the coefficient is 2 pi c over 24. This c is the chiral central charge of H states. So they're all very magical. You're using this non-abelian Barré phase, this abelian part, you can read off the chiral central charge of edge excitation. And so this is and also if central charge C is non-trivial, non-zero, that means you have a gravitational Chern-Simons term in the effective theory. Yes? No, they don't depend on it. So this, in this calculation, there is no rotation translation. So in principle, they are even for non-translation invariant system, supposed to work. Yes, yeah, and but I think certainly without translation symmetry, there's many other terms, like a curvature term. The coefficient may not be a constant. The curvature is already invariant. So you could have a curvature term with a non-uniform coefficient. But however, the Chern-Simons term, the coefficient must be constant, otherwise you lost the diffeomorphism invariance. So the Chern-Simons term is very, very special. The coefficient is quantized and uniform. But there's many other term you can add, which is locally diffeomorphism invariant, but that would allow even non-uniform coefficient. Exactly. For non-uniform system, when you have a curvature, you know how to extract them. But if you only know the integrate the value of action, that is a physical thing. If only from action, how do you know there's a gravitational term and there's a curvature term? Yeah, this became a very, very interesting issue. So from the action, from the value of action, how do you know you have this term or not? It becomes highly non-trivial. And probably eventually it's come to here. It's a vector bundle on the moduli space, and this actually is one of Chen number probably. This really maybe is more universal way, because we really worry about Chen number. The local curvature is not topological invariant. So this is a very good question, but one bottleneck in the more detailed formulation of topological order without translating symmetry. Yeah.
Question.
Yeah.
So the omega 3 is supposed to represent like an obstruction defining like a flat connection on moduli space.
Yes, that's right.
So why is it a 3 form? I would think you would just integrate like a 2 form or something.
Oh no, I'm sorry. This 3 form is in the space-time.
Yeah.
Not in the moduli space.
Ah, okay.
Yeah, and in the moduli space, it's a 1 form.
Sure.
And so it's really the S1. The M2 is a space. You know, this M2 is every point.
Right.
Then you go on a loop, and this loop promote the space into space times S1.
Okay.
And so this integration describes this the total phase of through one loop in the moduli space. That's one way to derive this.
The physical space is 2 plus 1.
Yes.
We focus on
2 plus 1. Yeah. So thank you. That so far I only do 2 plus 1.
and the fact that the truth sphere, that's the 2 the
No. This is just
it's
had nothing to do because these 2 spheres supposed to be moduli space, which is infinite dimensional.
complicated space.
Yeah, it's a very complicated. Yeah, I just because I don't want to give you a definition of fiber bundle, so I say I will replace the mathematical definition by a picture. So this is the picture is supposed to be a definition of a fiber bundle, what the fiber bundle looks like. So yes. Okay, for toric code we don't have this. So C equals 0 for toric code. And also you mentioned higher dimension. In higher dimension, say like a 3 plus 1 dimension, we don't have a gravitational Chen-Simon term. So therefore, in 3 plus 1 dimension, this picture works in higher dimension. But then this vector bundle will be totally flat, locally flat. There's no U1 terms. Yeah, that's what I believe. So basically, there's no central charge. There's a chiral central charge is something special in 2 dimension. And 6 dimension, there's something similar happens. So in 2 dimension, 6 dimension, and 10 dimension, you have chiral central charge. In other dimension, there's no such thing, chiral central charge. So so the theory is kind of different. Yes. Yeah, this is the Mohawk conductance. So it's a very mathematical way to describe the Mohawk conductance, which you can see they are quantized. But the quantized not as an integer, as a rational number. If you think about that, something quantized as a rational number, you know, what kind of mechanism give you such kind of rational number quantization? Yeah, well, that's a. Then now you can ignore this U1 part, concentrate on the SUN part. But the SUN part is flat, you know, when you go around the loop, there's no phase change. So you say it's trivial. But however, the moduli space have a non-contractible loops. So there are certain loops you can go through which cannot shrink to 0. So actually the SUN part can be non-trivial on those non-contractible loops. But what is non-contractible loops? Non-contractible loop is related to so-called the mapping class group of a torus. So let's do torus. Now let's concentrate on the torus, the moduli space for the torus. The mapping class group is that you can change the shape of a torus. Like from here, I can shear it. So now that you go through a loop, then you get this kind of torus. So that's you go on loop. But this torus actually is the same as the previous torus by changing the coordinate. They only differ. They're really the same shape, just differ by a change of coordinate. Okay. So So this coordinate transformation of torus, map torus to itself by changing its coordinate, is a form of group called mapping class group, and this is one of them. Another one is a mapping class group. You do this 90-degree rotation. That's another change of coordinate mapping torus to itself. So, and these two elements generate a whole mapping class group of SL2Z. So this 90-degree rotation and the Dane twist is a two generator of this whole mapping class group. And so that means we can go on the loop by connecting 2 points differ by mapping class group. It's just like this. We can do a loop, but this endpoint, initial point differ by a mapping class group. So therefore, the non-contraptile loop in the moduli space, it has one-to-one correspondence with the mapping class group. Okay. So therefore, say for this, if you go along this loop generated by Dane twist, then we have a matrix non-invariant phase we call T. Go around this big loop, you have this SUN non-invariant phase, so they have a T. If you do 90-degree rotation, you get another thing we call the S. And so this S and T is a quantized. At least if you ignore their overall phase, the SUN part is quantized, and the universal. So that's a topological invariance we can extract. So here we extract the C and S and T, these two topological invariants, these three topological invariants. And so certainly because ST form representation mapping class group, so they have this relation of this.
Question?
Yeah.
Does the moduli space have higher homotopy groups, or is it like a classified space?
Higher? I don't know. Yeah. I guess it has. Yeah.
What do you think they mean?
I don't know. Yeah. It's so all these are interesting questions. So actually, they are very, very important. Is the following. You can see. I describe the key is that it is a vector bundle over modular space classified topological phase. And here I only use pi 1 to describe a vector bundle. Maybe it's okay. Suppose SUN is flat. Probably pi 1 is enough to describe a flat vector bundle. Pi 1 is enough. Yeah. But certainly the other thing, the vector bundle can be non-trivial in other ways, not detectable by this pi 1. And then what that means? But certainly that means different phase physically, that's for sure. But that may lead to a different classification. So here we just make a brave conjecture. I suppose to say the vector bundle on this classified topological order, suppose this. But then I try to say that, this. So first, this is probably true. The vector bundle on all the Riemann surface, this is probably classified topological order. But here, the brave thing to say that we don't need to consider other space. Consider torus is enough. Just consider torus. And then we don't need to think about other things. We just think about the ST and C. So this is a very brave conjecture. We don't know it's true or not, but as a folklore looks like it's okay. So the conjecture is that this information ST and the central charge C, these provide a complete characterization of a 2 + 1 dimensional topological order. So this is what I mean by name. So we finally come up with a name, and once we have this name, and we can work on that. But we don't know what is proper name or not, because nobody proved this is characterize everything. So what do we do? As a physicist, we just go ahead, and even though we're not sure it's working or not, we just go ahead. Either everything works, then we are happy. We'll be happier if it does not work. Then that means by knowing what make it not work, then we probably can come back to see what we are missing here and what kind of additional information we should include. Otherwise we have no clue, you know. So we have this philosophy. We just go ahead and don't worry too much whether this is rigorous or not rigorous. Yeah. Yes. It works for both boson framing system. Yeah. So actually, so as a face, you know, so far we haven't find any contradiction yet. Yeah. Yeah. Hmm? Yeah, this part I myself is a little bit confused. Presumably, I should say the project representation module group to be more rigorous. But SL2Z have no project representation, so every project representation can be deformed into ordinary representation. So basically, the H2 is trivial. So maybe we can. So here, that's something I try to hide. You know, here I pretend S&T is a representation, but however, experimentally, we can only determine S&T up to the face. So we can only determine up to project representation, and so there's a gap. And but since there is no non-trivial project representation, maybe this gap is not a serious problem. And but certainly, if it's for some other group, if there's indeed a non-trivial project representation, then we have to be careful which project representation. So there's some, but here, yeah, there's something I don't totally understand. So now I just pretend this S&T is a representation. Yeah. Other question? So actually, there's a S&T. There's a easy way to measure it. So if you know S&T as a name, then we should say for every topological order, you should give me S&T. You know, so like a Torah code. What is S&T for Torah code? And what is S&T for double summing model? And what is S&T for Fibonacci? You know, so then that will give you a systematic labeling of all topological order. How to compute them? One way to compute them is to deform the metric, you know, compute the barrier phase. But this is hard. But usually, a physical system have a translation symmetry. When you have a translation symmetry, there is a simpler way to compute S&T. So let's just so the simpler way is basically is a following. So you just want to compute the overlap of the wave function, ground state wave function. So we have this x1, y1, you know, x2, y2, and etc. Then the overlap is that which I have not overlap, but here is like a x1 plus y1, then the x2 plus y2. We just do some coordinate transformation. So here I'm thinking about something like a quantum Hall states, so in the free space. This overlap is just an integration of xi, yi, you know. Okay, just some overlap. But since the ground state have degeneracy, so we have labeling, you know. There's a different ground states. We just then do this overlap. This is a very special overlap. You know, usually you just you don't change the coordinate just to overlap. But here we shift coordinate to overlap. But certainly once you shift coordinate, these two wave functions are almost orthogonal. They're very little overlap. It's just, you know, these two wave functions are locally different. So this overlap are exponentially small. Okay. So usually, yeah, this is almost like a useless overlap. But however, indeed, so this is you know, this is like we do 90-degree rotation to overlap. If your system have a 90-degree rotation symmetry, then this overlap is large. But however, if your system don't have a 90-degree rotation symmetry, you can still do this overlap, but overlap is very, very small. But then the magic is that if you ignore this very small factor and look into the volume independent part, So here the claim that this overlap is like a exponential, so the volume or area of a total system is in the exponent because the wavefunction is locally different. So there's such thing. But this term is something linear in the area, linear in area. Then the next term will be the like a L, but there is no L term. For somehow there is no L term. The next order actually is a zeroth order, so it's constant. So constant term is here. I write the constant term do not depend on L here. Then the other term can be 1 over L. So when system getting bigger, this is getting smaller, we ignore. So this constant term is a topological. And so this is a claim. And this is a S&T we look after. So therefore, we don't need to kind of barrier phase and integrate over a system, over a loop. You just do a direct. If you know the exact ground state, you just do direct overlap. You're done. That's it. And I think in one of the paper, like in this second paper, we calculate this overlap using tensor network. Actually, this calculation is designed for tensor network. You know, you can use tensor network to compute the overlap for quite large system, and then you can extract S&T matrix. And there's another thing wanting me to be more careful is that sometimes the ground state may carry different crystal momentum. Then they may cause trouble. So you may have to choose the proper size of the system. Hopefully, all the ground states have 0 crystal momentum. And then that may remove some ambiguity from the crystal momentum. And then you probably should get the right S&T, I think. Okay, so we did this computation, and for this Z2 topological order, which is basically loop gas. And the wave function is supposed to be 1. But here we modify it. We say the wave function is a G times the total length of a string. If a G is very small, that means we penalize the string. So the configuration with string have a low weight. If a G equal to 1, that is a Torah code situation. Every string have equal weight. We get the equal weight superposition of all string. However, there's a 4-fold degeneracy for Torah code on the torus. But this will only give you 1 state. The other 4 states have this funny thing is that the number of winding of string in x direction, or number of winding string in y direction, or in x plus y direction, this give us plus or minus 1 phase, depending on winding is even or odd. And this gave us 4 sectors. And then we just do the tensor network calculation. You write this wave function in the tensor network, then do the overlap. Then we see the phase transition as a function of g at around 0.8. Yeah. And so the when g is bigger than 0.8, the ST is this. This is ST. When g is less than 0.8, this is ST. What this means? And this means actually there is only 1 state. So here we pretend we have a 4 wave function. We pretend they are orthogonal. But when g is less than 0.8, this 4 wave function actually is the same wave function because there's almost no string running all the way around the loop. So there's no distinction. So if these 4 become the same wave function, then every overlap is the same. So we get this picture. But however, when g is greater than 0.8, indeed these 4 become orthogonal. So therefore their overlap gave you these 2 unitary matrices. Both are unitary. So this is SNT. Yes. We don't. And so actually this became an interesting question, whether there is a Hamiltonian exactly realizing. I think that answer is yes. Yes, there is a Hamiltonian realizing this wave function, but that Hamiltonian is gapped or not, we don't know. But that no longer commuting project Hamiltonian. And so this is always a problem. That for generic states we don't have exact soluble Hamiltonian. We don't know if it's gapped or not. Yeah. But I believe that this wave function, you can compute the equal time correlation function in space to see this wave function is short-range correlated or not. I think they are short-range correlated, but except at this point 8. At point 8, this transition is not short-range correlated. Yeah. And then we can do the same thing for the double Samian, except that we have same wave function, except we add another factor. The -1 times the number of loops, just stick these factors here. Then doing a similar calculation, then we see that there's a -1 here. Yeah. In this phase. Yeah. So this really say that yeah, this including this factor indeed change the phase of the change the topological order. It's a different topological order. And another thing to say that later we'll argue that actually the eigenvalue of a T matrix. Okay, there's one thing I have to say. The degeneracy on the torus equal to number of a particle type. You know, the torus code or double Samian have a 4 type of particle. You say it's 3. E, M, F should be 3. But the plus trivial one, we also include the trivial one. So trivial plus E, M, F. So we have a 3 type, a 4 type. So 4 type means the ground degeneracy on the torus is a 4. So the dimension of this matrix is same as the number of a particle type. Then if you diagonalize the T matrix, the eigenvalue of a T matrix happen to be the statistics of the rather more clearly should be topological spin of those each type. So here the eigenvalue is a 1, 1, 1 minus 1, means there's a 4 topological stage. 3 of them have a spin 0. 1 of them has spin 1/2. 1/2 is a fermion. Here is the eigenvalue is a 1, 1 I minus I. So it means the spin is a quarter minus quarter. So we have 2 Samian here. So actually, once you know this, you can know the Samian. And yeah, so this so this from ST you can read a lot. So I hope you know, for those who interested in tensor network calculation, you know, pay attention to this kind of overlap calculations. This is a very powerful way to detect all topological order in 2+1 dimension. Oh, physical fermion. I don't know. I didn't explore that. And but maybe let me just say one thing. For the physical fermion, you need to including the Z2 twist. Because when the fermion go around the loop, you have 2 choices: boundary condition, multi-periodic boundary condition. You should include that. If you do not include that, the information is not enough. But once you include all possible boundary conditions, and doing this twist is equally it works as well, yeah. But there's additional subtlety. But I myself is not totally clear. But I think if it work out, is information is there. Yeah. But that's a very good question. Okay, so once you have a name, so we want to make how to make a use of a name, because then the first use of name you can classify. You know, once you have a name, you can classify, and so for the crystal order, we know it's a symmetry. So from group theory, we can classify 230 crystal order in 3-dimensional space. And so now we want to do the similar thing for 2+1 dimensional topological order. But with this name, we probably can do it. And so how to do that? Well, it's pretty simple. You know, for every 2-dimensional topological order, we can come up with a STC. You know, so this way, we know how to do it. But however, can we pick arbitrary STC that would correspond to 2D topological order? That's probably not. Even if you require ST to be a representation of modular group, this SL2Z, even that probably is not enough. But at least, ST should be representation of SL2Z. But which representation are legal? Some representation may be illegal, some representation are legal. But which one is legal? So that's the main thing. We want to find a condition on those SNT. So that the SNTC, the data, satisfy those conditions. Those STC would correspond to topological order. Yeah. So this is very much like what Michael talked about. You have this F symbol describing wave function, the local relation of wave function. But if you have arbitrary F symbol, you don't get the wave function. Only F symbol satisfy pentagon identity. That gives you wave function, illegal wave function, stringlet wave function. So here's a similar thing. That's we want to find STC, this data, 2 matrix, 1 number. They set a certain condition. But then the main thing is what are those conditions? Okay. And okay, it's hard to find the conditions. So knowing their modular group is this is condition from the representation modular group. So at least those are conditions. But how to find other conditions? Okay. So here's some picture. To motivate to find other conditions, so let's consider an arbitrary Riemann surface, like a torus or genus 2 Riemann surface, and etc. Okay, so here I consider torus. And then I can deform the torus into this. It's like a sphere with handle. That's also torus. Okay. And then I can make this handle very, very thin. If you make a handle very, very thin, you can even almost remove it. It's like a sphere with 2 punctures. Or we can attach 2 handles, 3 handles to get other topology. So basically, and we can make all the handles very thin. You can get many punctures on the sphere. And so why you do that? So I try to say that then the property of those punctures kind of encode the property of the topology. So they are related. This picture I should say that the punctured sphere and the topology have some relations. That's it. So here on the switch gear, instead of study different topology with no puncture, want to study a simple topology like sphere, but with puncture. But what is puncture? Puncture are topological excitations, and that's it. So therefore, by study sphere with topological excitation, it's the same as a study this SNT, this fiber bundle, vector bundle we talk about. And then using this picture of topological excitation, we probably can come up some more conditions. And so once we come up enough condition, then we have a whole classifying theory. So actually that's so in next my lectures I try to push in this direction. Okay. So now let's concentrate on the excitations, which is the punctures. And so in the following, what I'm going to talk about in the following can be viewed as a systematic way to describe excitations. So what is the most general theory for excitation in the gapped states? And another way you can say that this is a general theory for non-abelian statistics. I think you heard a lot about the non-abelian statistics, but what is non-abelian statistics? Again, it's a name. There's a type A, type B, type C non-abelian statistics. But then the first question is that what is the data to describe a non-abelian statistics? So we still have this issue of naming. So what is the data that is required to describe a non-abelian statistics? So in the following, I will try to again describe some physical situation, try to come up with the data which describe non-abelian statistics. You can see so far we come up with the data SNT and C to describe ground state. That's one idea. So now we want to come up with data to describe non-abelian statistics of excitations. But how to do that? So what is the statistics? What is the excitation? And we know what is excitation. There's a bump. But there's a more formal or more rigorous way to define excitation in gapped states is the following. So we have a Hamiltonian which gives us ground states. Then we add traps at different location. So here we have a trap at the position Kc. We may have another trap at the position Kc prime in some other place. We add the traps. Those traps may trap excitation. So that means that we want to find the ground state of Hamiltonian with trap. So ground state of Hamiltonian with trap, that wave function corresponds to excited state, some wave function with excitation. Okay. And then it's very important that we design our trap in such a way that the Hamiltonian with trap also have a gap. So there's a gap and there's something, maybe the degeneracy below. Okay. So therefore this psi exc describe this subspace, the ground state subspace of Hamiltonian with trap. And this is one of the most important concept in defining topological excitation. So this ground state subspace as function for trap location, you can see, and this is the object you want to study, and you want to extract this data for non-abelian statistics from this object, from this again from the ground state subspace, but with a trap. Okay, any question here? Then once we have this ground state subspace, now we can define so-called what is the local quasi-particle excitation, some local excitation, and that is simple. Suppose we have two subspace, one subspace. Okay, maybe let's put it. Suppose we have a subspace with a trap at a Kc prime, etc. And this subspace can be obtained from another subspace without trap at the Kc. We don't have trap at the Kc by applying a local operator near Kc. So that means whatever the trap created at the Kc can be simulated by a local operator. If this can happen, we say this trap only trap a local excitation, like a spin flip. So that's a trivial excitation. Okay. Now with this definition, you can see that topological excitation is something like this trap indeed traps something, but no local operator can remove it. Yeah. So now from this we can see, yeah, this is local and topological. And then we can also say that suppose we have two different trap, this different trap, but this trap only differ at the Kc. Other trap are the same. Only at the Kc we have different trap. Then we have then first trap give us one subspace, another trap give another subspace. However, if you can continuously deform first trap to the second trap without closing this energy gap, then we say that these two topological excitation are equivalent. So that we define the equivalence relation. So before we label excitation using trap. So for every trap we have excitation, but the trap is very complicated. This is many parameters. So we want to build equivalence relation so that we have only a few types. So one way to build equivalence relation is that we say two trap Hamiltonian are equivalent if they can deform into each other without closing energy gap. So once you do that, the most trap Hamiltonian are the equivalent. So only a few different types are inequivalent. So this gives us so-called a different type of a topological excitation. So this is a more rigorous way to define topological excitation. Certainly another way is to compare the ground state subspace. If ground state subspace of two topological excitation can be mapped into each other via the local operator at position Kc, then we say the excitation at Kc are same type. So that's this one the same thing. Okay, so that became a definition of topological excitation without symmetry. But if Hamiltonian have a symmetry, or if you want to study symmetric system, this definition can be easily adjusted to the case with the symmetry. We just require the trap Hamiltonian to have a symmetry. Trap also have a symmetry. And when we define equivalence relation, we also require this equivalent local operator have symmetry. We say the two excitation are equivalent if they can be connected by symmetric local operator. When we have symmetry, we do that. Yeah. So this basically is a foundation of a topological excitation. Then using this setup, we basically can develop a general theory of a topological excitation. The general theory turns out to be so-called a tensor category theory, or fusion category theory, or braided fusion category. So you can view this as a physical way to introduce a fusion category. So what is a fusion category or braided tensor category? Here, that's it. This is a category theory. So this is really a category theory. Okay. So there's something which is very important in category theory, but physicists usually ignore it, and which is so-called composite and simple. Okay. So there are some excitation is composite and some excitation is simple. So what is simple excitation? Remember, excitation is a trap. Every trap corresponds to excitation. So you say, which trap is a simple excitation? The answer is that if the trap have a stable ground state degeneracy, then it's simple. The stable really means that, remember, when you have a trapped Hamiltonian, we have this kind of spectrum. We have a degeneracy. However, if you modify the trapped Hamiltonian near this Casey point, we just modify them, deform them, that we cannot split degeneracy by local modification, then we say that trap is stable. Usually, this is what we have. When you have a trap, we don't have an accidental degeneracy. They're always stable, But the mathematician is very careful. They include the possibility of accidental degeneracy. When you have a trap with accidental degeneracy, when you add a little perturbation, they will split. So that's it. The simple excitation is what we call excitation. And the so-called composite excitation is what we call the excitation with accidental degeneracy, or trap with accidental degeneracy. So that is this picture. So this is a trap with accidental degeneracy. If you add a little bit of perturbation, they may split into this spectrum where R and J have no accidental degeneracy. So then we say R alpha is composite type. We write R alpha as a sum of R and J. Yeah. So this is a sum in Anya. If you read something, there's a sum. But most people write sum as a plus. Then when I first learned this, I say plus. I thought it's a wave function amplitude quantum mechanical superposition. Then I don't understand what's going on. I'm really just totally confused. And so now I realize that this is not plus as adding two vector. It's really it's more like it's a direct sum of two matrix. It's a two block putting together. So if you're careful, this is better. It's conceptually, it have nothing to do with the superposition principle. Just a two block. It's really this picture. This is a picture. The splitting of accidental degeneracy is this from composite to simple type. So actually, every composite can be written as this. And physicists take this for granted. I never studied composite. I always studied the simple one. Physicists always study simple one. So we don't worry about composite. Okay. And another thing I want to say that this ground state subspace have a name called the fusion space in category theory. So I would later, from now I would using this symbol to describe the same thing. And then we also say that the fusion space, we don't care where it is, because the location of a trap is not very important. The more important is what kind of excitation is trapped there. So type of excitation in the trap is more important. So therefore, we kind of ignore their location, only keep the type information. So I write fusion space as only have a type. So type I1, type I2, they together, and we have a trap which trap I1, I2. The ground subspace of those kind of trap is so-called a fusion space, which is a function of only type here. Yeah. Okay, so this is basically is like a introduction of the basic ingredient of category theory. Actually, one can describe all this using point and arrows. That's what I told. What is category theory? It's points connect by arrows. It took me 5 years to to know what is point. And but one can use point and arrow to describe all this. But I tried. I have transparent for that. But then it's too abstract, so I ignore this. So I use it in this more physical way. And one very important ingredient in category theory is fusion. So this is the fusion category. So far we're not talking about the fusion yet. So below this line, the feature we talk about is a category theory. You can see for the category theory, we don't need a space. We don't need a dimension. Even one point, a quantum mechanical system has these features. Have degeneracy, have split. 0 dimension, 1 dimension, 2 dimension, all have these features. So those features are category. This is a category theory, which have a concept of a simple and a composite excitation. So that's a concept of category. And now we want to do something more. We want to study one-dimensional system or higher. When you do one-dimensional system, you have a new concept, which is kind of fusion. There's a new operation called fusion. So fusion means that in higher dimension, in one dimension higher, we could have a excitation like I1, I2, which are very well separated. We could have that. So therefore, we can have a well separated excitation. But then we can bring two excitation closer. We can only do that in one dimension and higher. If the two excitation are very well separated, yeah, we have a fusion space, which is like this. We have degeneracy here. But when you bring two excitation closer and closer and view them as a one excitation, then when you bring them together, then you'll find they may split. Because the two excitation may have an interaction between them, this degeneracy may split. So the degeneracy split means the following. If you view two excitation as one excitation, you are allowed to add a perturbation which connecting the two, because you pretend these two are close. You have Hamiltonian interaction between the two. Before, when they're very well separated, we know that this degeneracy is robust against any perturbation near one point. Against any perturbation near another point, suppose I and J are simple. But however, the degeneracy may not be robust against perturbation cover both points. So if you add a perturbation which cover both points, or bring 2 points close, they may split. So that means if you view Ij as a single excitation, they are not simple, because Ij is a very special trap. So one trap here, one trap here. View these two traps as one trap, but this is just a one very special trap. And you can have a other more general trap, one trap, and then may cause a split. So this is very natural that they may split. And then this split the space. This degeneracy here correspond to, they are stable. They correspond to simple type. So there's it's a decomposition of a vector space. So we have this, so we can formally have this Ij fused together became a composite one, but have many simple type, just like alpha. So that's a sum, and that's it. So this is a physical explanation of a fusion of anyons. The fusion of anyon is a fusion of two traps, and the sum is a splitting of a degeneracy of the trapped Hamiltonian. That's it. So that's this is kind of physical interpretation of the so-called fusion ring or Grothendieck ring of this. So again, this is a feature of fusion space. If you know the fusion space, these structures are there, and so this is kind of. But however, sometimes this K1, K2 can be the same, can be same simple type. So if they're same, we just have a factor 2 in front. So we simplify this using the Nijk, a sum over K, So this Nijk is like a fusion coefficient, and define the fusion ring. Define, when you multiply ij together, what do you get? So this Nijk is the data, that's it. So this is the new data from the quasi-particle. From ground state, we get SNT. Now from quasi-particle, we get Nijk. Yes.
So this is kind of pedantic, but when you say fusion ring, presumably the inverses are like the dual representation, right?
Yeah, there's a so why inverse always exists? That's the question.
I mean, you're calling it a ring. Well, in what sense is it an inverse if I tensor I star is not always just one plus one stuff?
If they contain one, I don't know what's a maybe ring. I don't know. It's a the ring. I don't know what in which sense kind of ring. I kind of there's the multiplication. There's the inverse.
Presumably adding is like.
Yeah, but the I don't know. Yeah, this I just what the I do know every particle have its dual, but whether that's a I had a wiki. What is the definition of ring to answer your question? Additive have inverse. The multiplication is
What's the inverse of the direct sum though?
No, the formally there's a inverse. Here Nij all positive, but the formally, they are very formal.
It can't be negative though.
It cannot be negative in real case, but formally you can have this. It's very formal. Yeah.
So you allow for like negative
Yeah.
multiplication.
Yeah. What I really try to say is that the data is really just this Nijk. And when you deal with Nijk, you can pretend as a linear algebra with integer field. But that's just a formal thing, And so a lot of calculation here involving like the vector space within the integer field. This is very much like vector space in integer field. But in that case, the additive this became a negative means something, but not in the physical interpretation. Yeah, indeed that's true. Yes. Yeah. Well, no, just look at this. You have two traps. You bring two traps together and back. Yeah. So the let me see what it say. Okay. Suppose you have a two particle very well separated. Then those levels are very very close degenerate. You may pretend you have a density matrix which are constant on these levels. And when you bring these two particles together, now you have a split in certain way, depending on how you bring them together. Then you wait a while, the density matrix no longer constant on those levels, maybe more constant on here. And then we'll make them apart again. Then you have a different density matrix in the degenerate level. So actually that's a one way to prepare a particular state on these degenerate states. Yeah, you suppose, because at the beginning they are all degenerate, you don't know how to prepare a state here. One way to prepare a state here is to bring two particles together and using this degeneracy to prepare a state here. Then you separate them. Then you have a not boring constant density matrix. I have non-trivial density matrix in this level. So that's kind of this kind of thing is preparation of a qubits. Yeah, that's one way to do that. Okay. Then there's but not arbitrary integer tensor would give us a fusion ring. Again, this n has to satisfy certain conditions. The condition is that fusing I, J, K together should give us the same thing, regardless how you fuse them. So you can fuse Ij first, and then fuse the product Ij with K to get a bunch of L, But how many L do you get? We get Nijkl is this how many L I get. But however, if you fuse differently, I fuse Jk first, then fuse the product of Jk with I to get a bunch of L. We should get the same number for L. And so this is the relation. So we fuse Ij into M. But how many different ways to fuse Ij into M? That's this number. And for each M, we can fuse this M into K. And how many L I produce from this fusion? That's a MKL. Then multiply these two together means that I fuse Ij into M channel, the M fuse into K into L. Through this M channel, how many L do I get? But however, Ij may fuse into M1, M2. There are several different M. So we have to sum over all possible intermediate channel. Then we get total number of L I get. So that is the meaning of this. Or you can do the other order. We can fuse Jk first into N, then fuse N and I into L. Then this tells me how many L do I get through these different N channels. And these two should be the same. And so actually this gave us this identity. So this is the condition Nijk has to satisfy. This is a very, very important condition. Okay. But actually there's more. So I describe this fusion in the same way. Suppose we have a 4-particle IJKL, L star on the sphere. Okay, we have IJKL star on the sphere. Okay. Then on the sphere, we have this 4-particle. Their fusion space is this big thick bar is their fusion space that degenerate. Okay. If I fuse Ij together, I bring Ij together, they may split. They split into different M's. So that's I try to describe what I said in the picture. And then this M may fuse. Then we bring K near this Ij bound states. Then each M may further split into this bunch of L. Each line is L. Okay, the bunch of L. Okay. But here I want to emphasize, this picture is like choosing a basis. Here I have degenerate vector space. Then I split it into several subspace and picking there's some natural basis. Okay. So it's easier to explain in the picture. So those are labeled the basis. So that's a one basis. So basically, this picture really says I fuse Ij first, then fuse K, then fuse with K, we get the basis. They are labeled by this M. So then this basis, different choices labeled by the M, and also labeled by some additional factor, because we may have several M. If you have several M, same M, then they may kind of rotate around each other. So there are some index. So this alpha index is when Ij can fuse into several same M. That means if Nijk is not equal to 1, Nijm is not equal to 1, we have this alpha. If Nijm is always equal to 1, there is only one way. We don't need this alpha. But anyway, but then we can also do another fusion. We can fuse Jk first, split into N channel. And then fuse I with N, then split further. So this means another way to split the same vector space. Just two different ways to split same vectors into blocks, into subspace. And there should be a relation between these two bases. There are two natural choice bases using different way of fusion. Okay. And yeah, that's F symbol. So this is another place F symbol appears. And here I write F symbol in a more general way compared to what Michael did. What Michael did is assuming Nij always equal to 0 or 1. So we don't need this alpha index. So then you just Ijk MNL, you know. And but if Nijk can be 2, 3, then there's an additional complication. So we have this additional alpha index. Okay. And in this language, these IJKL are fixed. Okay. And this M, this 2 alpha, and N and this 2 alpha, these 3 index label one basis because L is a fixed actually. So these 3 index label one basis, L is fixed, and these 3 index label another basis. So it's really the transformation between this index. So actually, the self-consistent condition, this condition ensure that these 3 index, this M alpha alpha and N alpha alpha, they label they have label same dimension. They have same dimension. These are 3 index, but they have same number of choice. Okay, so this is square matrix, and because they are different splitting of the same vector space, so this is unitary matrix. So so unitarity is pretty natural here because here we are really talking about a ground state, talking about the physical eigenstates or states. So here is a unitary. So what I really try to say is that this Nijk is not enough to describe a fusion. You know, I wish it's enough. Actually, this F, I really hate F, and but it's not enough. Unfortunately, it's not enough. You know, unfortunately, not enough. So we have to dig more, and one way to dig more is to do this to see how the fusion, how the splitting, different way of splitting, how their bases are related, and because this condition only says that the different way of splitting gave rise to same dimension here. So these 2 spaces are same dimension. They also their dimension are same. Now here we will also compare the bases. Their bases can be compared via this F symbol. And I think probably is a claim that this Nijk plus F is a full description of a fusion. So that's the full data to describe a fusion. Yeah. Okay, I will stop here. Yeah. Any question? Yeah.
Can you always choose a gauge where F is unitary, or are there reasons to look at non-unitary?
In this case, it's always unitary, because I just do this splitting.
Right.
Yeah. And because what I try to say is that, okay, yeah, you can see what we do here is like a physicist way to do it. It's still constructive way. You know, it's not like we have abstract things with some specify some condition. But if you construct using this many-body system, so here I try to argue you only get unitary F. So that's maybe connection with the mathematicians that maybe only unitary F have relation to the many-body system. Yeah. Yes.
I've always been confused about whether how you would define it.
No, I don't know. So that's why I say I hate F. It's we need more informations. But certainly this the F contains a lot of unphysical things. Yeah. So it's not like S and T. You can see this is a very, very good question. You know, here at least for translation invariant system, I gave you a recipe to compute S and T. So S and T are kind of directly physical. Yeah. And so for the F, maybe you can see this using the fusion is also a way to do that. Is the way I described here. You view as a physical way to measure f. But certainly there's a lot of what should I say? There's a lot of freedom we have to quotient out. For the SNT case, the freedom are easy to quotient out. It's just a unitary transformation. And here the freedom, maybe there's more. Yeah.
Like for example, you probably want to define it as a way, the split
Yeah, exactly. Yeah. Yeah. Exactly. There are many different phases, and actually, the more actually this condition is highly non-trivial. I'm kind of cheating here because in general we have ijk and a bunch of many other particles. Actually, so that's this dot means there's a many index coming from other particles. Here I assume somehow I can fix them. So those particles are not moving, is not moved. And then, so actually this F symbol not just related this dimension, related to very high dimensional vector space. But there's a claim that this very high dimensional vector space have a block structure. And each block are related to F. And every different block are related by same F. So there's something quite non-trivial here. Naively, you may worry about the different block have a different F, then it's become out of control. But here, say, there's only one F. Yeah, and so I will talk maybe tomorrow. So this F actually is a 6J symbol. And so tomorrow I'll give example using a group example. Then in this case, F is exactly a 6J symbol. Yeah, that's right. Yeah, that in that sense is similar. Yes. Yes. One dimension. One dimension. First, one dimension have no topological order for boson system at least, and then the open bounding and closed bounding is a very good question. And so here actually I only consider closed space without boundary. When you have a boundary, I don't even know how to define gap. When you have a boundary, because a gapless boundary can have a gapless extension, so this gap being closed. Then you have to be very careful. Say, oh, those the lower lying one is only at the boundary. Then you have to really specify they are at the boundary. But what do you mean by at the boundary? Is a centimeter away is at the boundary, or millimeter away is at the boundary. So there's all kinds of subtleties. So I try to avoid those by consider only closed space. Yeah. So the idea here is that by consider all kinds of closed space with different topology, I should extract information for topological order. So basically, using the different topology of space as my probe, using that to extract the information topological order. But this picture really say that and the topology, the space with different topology and the sphere with many puncture roughly the same. So we can do a similar thing by study punctures. Yeah. But not boundary. It's not in that case. There's no from this point of view. There's no degeneracy. Because on the ring, there's no degeneracy. We don't think about the boundary. Yeah, but that's regarded as a gapless edge extension, which we don't talk about here. We try to avoid. And so this is really, so again, this is a very good point. The picture I try to present here is a picture only bulk. We try to quotient out all the edge consideration. So by this philosophy, this the boundaries in 1D chain is a quotient that we don't even look at it. That's then can you tell the difference? So actually, this became really, really interesting. Yeah. Yeah. Could you be louder? Yeah. That's right. It's just different name. They should be really called different name. You know, it's so yeah, there are, but yeah, they are related. I think I need to relate them, and so I hope in next lecture I can get there, and yeah. So basically, what I'm going to do is that right now I'm trying to collect the data which describe non-abelian statistics. We already see one, NIJK, and also F symbol. So we will collect two data. And there are some more data. And then after collecting all the data describing onions, then those data should have a self-consistent condition. We have many conditions. Then we want to relate this non-abelian statistics data with SNT data. Then combine all the conditions together. So that's the strategy to get many conditions. And we hope by doing this we get all the conditions. Then we can have classifying theory. Yeah. So later I will do that. So the reason I can present this is that I can do this without F and R. So this is something much simpler. And although I introduced the F because Michael did, so otherwise I don't need to introduce F. Yeah. Other questions?